presenting Green Island Observatory.
Hi everyone, my name is Yenal Öğmen. I have been observing variable stars at my backyard observatory since 2005. I sent the data I collected from my observations to various organizations, networks, and collaborations around the world. Up to now, I have discovered 3 variable stars, and my observations are published in 18 papers. In my talk, I'm going to give you a brief information about one of my favorite targets that I observed in my observatory, which is also the widely observed class of variable stars among astronomers. Dwarf Novae, which is a class of cataclysmic variables. This was part of my dissertation for my astronomy degree I completed 2 years ago at University of Central Lancashire. So first let me define what cataclysmic variable is. So observations show that more than half of the stars are part of a system of 2 or more members. So in binary systems, which are composed of 2 stars, we call the primary and the massive one primary and its companion secondary. So the primary, this massive one, evolves faster into a red giant phase and expand to a point where further expansion then results in a mass transfer from primary to secondary. And the mass transfer rate is increasing in time, and this significantly decreases the separation of stars and loss of most of the hydrogen envelope of the primary to its companion secondary. Therefore, during this stage, the lower mass companion gains mass, and the massive one turns into a white dwarf, which is a very compact object about size of an Earth, but very dense, which is composed of mainly electron-degenerate matter. So eventually, their separation becomes not much greater than a solar radius, and their period, which was once a few years, now becomes only a few hours. So all of these vast changes occurs in these systems in a time scale as short as 1,000 years. So at the end of all of these processes, if the masses and separations of stars result in a mass transfer from secondary onto a white dwarf in the opposite direction this time, we call these systems becomes a cataclysmic systems. We call them cataclysmic variables because the eruptions we see at these systems are so huge that it can brighten the system up to millions fold. There are several classes of cataclysmic variables, and Dwarf Novae is one of them. Now let me define what Dwarf Novae is. So, in cataclysmic binary systems where magnetic field strength is very weak, the transferred mass forms an accretion disk around the white dwarf. Because in the presence of magnetic field, this transferred mass follows magnetic field lines and land on the white dwarf at its poles. Therefore, we call them polars, which is another class of cataclysmic variables. So, in this case, in Dwarf Novae case, we don't have significant amount of magnetic field, so we have accretion disk around the white dwarf. So, due to instabilities in the disk that I'm going to talk about later, accumulated matter makes sudden dumps onto a white dwarf, which releases huge amount of gravitational potential energy, and we see this as an eruption. We call them Dwarf Novae eruptions because they are not as powerful as their cousin classical nova, which is another class of cataclysmic variables that is a really powerful event due to thermonuclear origin of the eruption. The recurrence of Dwarf Novae is from a few days to a few decades and can brighten the system by 2 to 5 magnitudes, which corresponds to 6 to 100 times in brightness. So, since the origin of these eruptions is the accretion disk, Dwarf Novae are considered as an important object to study accretion disks, Since we see these disks everywhere in the universe, like around black holes, around young stars, etc., studying them shed light on formation of structures in the universe. So it is really important to observe dwarf nova in this regard. There are three classes of dwarf nova. I'm going to talk about the most interesting one, which is UGSU type dwarf nova. This is the schematic light curve morphology of this type. These stars exhibit two kinds of outbursts, normal outbursts and super outbursts. Normal outbursts last shorter and they have slightly smaller amplitudes. Their recurrence time scale is unique to each system. On the other hand, super outbursts last longer and they have slightly larger amplitudes. Super outbursts are widely separated in time, and usually there are several normal outbursts between each successive super outburst. A cycle from one super outburst to the next is called a super cycle, which is about a few hundred days long for a typical UGSU system. So the question is, why do we see two kinds of outbursts at these systems? Astronomers were very curious about this. This is the temporal evolution of a typical UGSU system according to the most successful model designed for these stars, thermal tidal instability model. So, according to here, you can see how the line curve of the system changes in time. Here you can see radius and mass of the disk changes during a supercycle. So, according to TTI model, mass transfer rate is constant from secondary to white dwarf. So, and this causes a significant increase in the mass of the disk, where the accumulated matter piles up on the outer disk, and when it reaches to a critical size, temperature suddenly increases, and this increases the viscosity in the disk. And this is the point where the normal outburst, as you can see from here, these are all normal outbursts. This is the point where normal outburst sets in. High viscosity causes the material in a fast manner to flow inwards towards the white dwarf, which releases gravitational potential energy that powers the normal outburst. For this reason, the origin of the normal outbursts is the thermal instability. When a normal outburst occurs, as you can see again from the diagram, some of the material is ejected out of the disk. So, however, this does not halt the growth of size and mass of the disk. Sorry. This means each normal outburst, as you can see from here, they are increasing in radius and mass. Each normal outburst occurs at a disk which is slightly larger and heavier than the disk of the previous normal outburst. But this growth cannot continue forever. There is a critical size for it, and according to the TDI model, it is 0.46 times the separation of stars. And when this reaches this size, the outburst occurs as a super outburst. Why? Because it originates from the most massive disk. Because when this reaches this critical size, it becomes vulnerable with the tidal interactions with the secondary star. So tidal instability appears, and this causes the outburst to occur as a super outburst. Then super outburst settles the system back to normal level in radius and mass. So now let me show you some real data. This is the light curve of V1504 Cygnus, showing the super outburst in November 2010. Here in the upper pane you can see two normal outbursts and the super outburst in between in November 2010. In the lower pane, you can see the zoomed part of the upper pane shown with this gray rectangle. Can you see these waves? These are called superhumps. They are small amplitude periodic brightenings which appear mostly when the super outburst is at maximum and fade at quiescence. So, what causes these superhumps? It is important to understand their nature because now we know that we can use them to understand the observed system better. Now let me explain you the origin of superhumps with a simple diagram. Let the central white circle be the white dwarf, the upper one be the secondary star orbiting the white dwarf with an orbital period, and the brown circle around the white dwarf be the accretion disk. So as time passes, this gets bigger. Why? Because of the accretion. But when it reaches to a critical size, the gravitational tag of the secondary distorts its shape into an ellipse. And this elliptical shape, due to again this interaction, rotates very slowly around the white dwarf. And we call this period precessing this period. So since this rotation is very small, the period of the precessing disk is significantly greater than the orbital period. This is an important fact. So, according to the TTI model, superhumps that we saw in the previous slide, those waves, small waves, are the result of this interaction when secondary star and the disk and the major axis of the disk, let's say, align like this as shown here. Okay? So what happens when we see superhumps at this point is that secondary star resonates with the orbiting material in the high viscosity disk. This increases tidal stresses, which deforms their orbits into a non-parallel elliptical orbits. This causes orbital intersections, and colliding material periodically brightens the disk, and we see that as a superhumps, those small waves. So after they are each lined up like this, secondary star needs to move a little, slightly further along its orbit to align like this again. Why? Because the elliptical disk also rotating. For this reason, the superhump period is a few % longer than the orbital period. So, in November 2010, another UGSU star was observed to super outburst. It was HD Cassiopeia, and I was able to follow this super outburst at my observatory. And this is my 5 hours light curve at my observatory. Can you see those dips? These dips represent the eclipse of white dwarf and disk by the secondary. So, since the separation of stars in cataclysmic systems is very small, we mostly see these eclipses on their light curves. And therefore, eclipsing dwarf novae are especially important for astronomers because the time between each successive eclipse gives the orbital period, which is a really important parameter for these systems. So, after 2 nights, I have this light curve. As you can see, there's a significant changes on the light curve. Now, in addition to eclipses, now we have superhumps, which occurred right after the eclipses on this night. Please notice here the amplitudes of the superhumps. As you will see later on the next light curves, they will gradually fade away. After another 3 days, now I have this light curve. As I just told you, you can see that superhump amplitudes go smaller, but you can also notice that they occurred slightly later on this night. This is the result of the fact that the superhump period is a few % greater than the orbital period. For example, for this system, it is only 4%. So, this is exactly what the TTI model predicts and proves that the origin of these superhumps is the slowly rotating elliptical disk. So, after another 3 days, I have this light curve, and here you can see that the super amplitudes got really smaller and they occurred significantly later than the eclipses. So what can we learn from these parameters that we obtain from the light curves? As you can see, we can calculate superhump periods from the superhumps, the time between each successive superhumps, and the orbital period from the eclipses. Astronomers derived this formula, which relates orbital period, superhump period, and precessing this period. So we can calculate the period of precessing this, since we know superhump and orbital period from the light curve. We can also use these two values of superhump and orbital period with this formula to find the Q parameter of the system. Q parameter is the mass ratio of secondary to the primary. So I think it is really fascinating to be able to calculate all these parameters from just the visual light curve of a UGSU star during its super outburst. Here I want to show you my results for the analysis of 2010 super outburst of HD Cassiopeia. For this, I downloaded all the good quality photometric data from the American Association of Variable Star Observers to supplement my own data. I analyzed all the light curves and found the mean orbital period and precessing this period. Then I used the formula I gave in the previous slide to calculate this period, precessing this period, and the mass ratio of the stars in the system. These results agree with the results accepted for these systems and are very close to the values obtained by Bakowska and her colleagues. As one last thing, I want to show you this image. The marked star is HD Cassiopeia, this one. So you can't see both companions here. Not even you can't see the disk either. And I took this image in January 2017 during its last observed super outburst. Here I want to say that it is really amazing to be able to calculate all these parameters because you can't see the stars and disk itself. So you just measure these tiny spots, brightness changes over time, and you can find a lot about the nature of the system, even by using a modest equipment. Thank you for your attention. Any questions? Any questions? Yes.
Yeah, it's nice to hear that you have an observatory in Cyprus. Actually, one of the universities here should really build an observatory and a planetarium, which I had experienced when I was in Çağ University, Tarsus. When I was invited to do this, we established a planetarium and an observatory and research center at about $100,000. I mean, not very much. But after that, I mean, university really gained a lot of attention from the surrounding, and therefore it's also a public relations investment.
Yes.
I really appreciate your and Aysel Hanım's efforts. Although you still did not reach somewhere, I'm sure someone will catch the wave and go with them and really make Cyprus really more enjoyable place with planetarium and with observatory, with more students, with more people observing the skies and learning about them. I really thank you and Aysel Hanım for all your efforts.
Thank you very much. Yes, you are right. And as you said, it is not, you don't need to invest much to have a good observatory and do some scientific work with the sky. For example, with my first telescope, 12 centimeters, I got my code for my observatory from the International Astronomical Union. So you can do, with a really small amount of money, you can do everything, but you have to have a vision first.
Thank you.
Any questions? So let's clap Yenal Öğmen.